CarbonInspired 2.0 is a European network of nanomaterials whose objective is the transfer of knowledge to the southwestern European industry. This network was born thanks to an initiative created in 2010 by the founders of the network and coordinated by the Galician Automotive Technology Centre. This project is co-financed by the operational programme Interreg IVB SUDOE through ERDF funds. CarbonInspired 2.0 provides you with a website with transfer tools that will help you understand the value added of nanomaterials and the best way to integrate them in your products and processes. First, this network provides you with a technology observer daily updated, an e-learning platform, a debate community in LinkedIn, one blog about nanomaterials, industrial workshops and seminars, a quarterly newsletter and news. Moreover, partners from CarbonInspired 2.0 have developed 5 prototypes to demonstrate the functionality of nanoparticles. Nanomaterials can provide textiles with new functionalities that allow them to respond to external stimuli with a totally surprising way. CTAG, within CarbonInspired 2.0 project, has developed a prototype of heating material that demonstrates the enormous advantages obtained with the addition of a tiny amount of nanoparticles. For this prototype, a textile substrate has been embedded in a resin with nanoparticles and several additives. The prototype has shown a temperature increment within the range from 15 to 50 degrees Celsius and even higher, working with security voltages. The direct application of nanomaterials to the textile allows to homogeneously distribute the thermal flow along the whole surface of the fabric. In this comparison, it can be observed that solutions currently available in the market are based on resistive circuits that do not provide an optimal heat distribution. The use of nanoparticles helps to solve this limitation. The developed mixture can be applied through several technologies such as deposition, screen printing or pad printing, being adapted to different substrates. Furthermore, it's an economical solution since it's possible to regulate the voltage and therefore the heating emission. These flexibility and versatility allows it to be integrated not only in highly technological applications but also in conventional products where the thermal emission can be an added value to the design. One of the most important drivers of growth in transport and leisure areas is the maritime sector. Its components must provide a high useful life to assure the correct service over the years without a loss of properties. Therefore, it's necessary to protect surfaces from algae, microorganisms or salts, as well as from corrosion of salt water. For that purpose, Aimplas, within the frame of CarbonInspired 2.0, has developed a coating with anti-fouling properties based on the action of several nanoparticles. The development begins with the selection of nanoparticles and their incorporation into resin using a 3-roll calendar at low contents, being that an advantage comparing with micrometric additives. After achieving a correct nanoparticles dispersion and distribution in matrix, coating is applied on piece by an easy step. Afterwards, coating is cured by thermal action, resulting in an optimal protection against external agents. With the objective of testing coatings under real environments, they were exposed to seawater with a microalgae inoculum. After a period of 45 days under controlled conditions of temperature, light intensity and nutrients, it's possible to detect by a microscopy analysis an algae and several microorganism growth in testing water. When comparing surfaces, it's possible to distinguish the presence of algae deposits in sample without coating. An electronic microscopy analysis shows how the developed formulation avoids the presence of algae and salts generation, characteristic of fouling, ensuring a higher durability of material.
Thermoplastic injection molding is a process by which we produce a great part of our daily goods and is now being adapted to produce very small parts with precise features. The direct miniaturization of the process isn't possible due to the wear of the microshapes that such parts detain, or to the reduced quantities of polymeric material that is injected. The use of nanocrystalline diamond coatings on the molding surface, presenting high hardness, thermal conductivity, thermal shock capacity, and low friction, may assist the molding tools for the production of enhanced polymeric microparts.
Nanocrystalline diamond films exhibit high hardness, thermal conductivity, thermal shock capacity and low friction coefficient and can be coated into a vast diversity of substrates on a chemical vapor deposition reactor. After the preparation of the surface to be coated, where proper mass can be applied to grow the film according to a selected geometry, the moulding block is placed in the hot filament chemical vapor deposition reactor. The system is closed and the vacuum pump is turned on to evacuate all the atmospheric gas from the chamber. The precursor gases, in a proper balance, are turned on and the deposition pressure adjusted. At the same time, the auxiliary substrate heater is turned on. With the deposition atmosphere stabilised and the moulding block preheated, the filaments are gently powered to the deposition temperature. Deposition conditions are monitored and adjusted if necessary during the deposition process. The deposition time is dependent of the desired film thickness. The growth rate is about 100 nanometers per hour, and for this application a film of about 500 nanometers is necessary. A moulding tool was prepared in order to compare the polymeric flow in a diamond-coated path and in bare steel. The flow throughout the diamond path faced less drag as concluded from the polarized images taken in a transmission optical microscope. Deicing is a well-known phenomenon in aeronautics. Main consequences are the modification of the aerodynamic profile of wings aircraft, where icing is occurring most likely, and even more motor extinction.
That is why ADERA, within the framework of the project CarbonInspired 2.0, decided to develop a cutting-edge technology based on heating paint, in order to provide an efficient and optimal de-icing solution. In order to achieve this challenge, ADERA requires the expertise of Rescol, a company specialized in private research in polymer area. The two companies associated their competencies in order to achieve a successful development of this new paint.
The paint itself will be electrically conductive and will provide the necessary heat for the efficient de-icing. Let's talk to Mathieu Oyacabal, who is specialized in this technology.
To formulate these conductive paints, intrinsically conductive polymers like polyaniline might be used. And when a voltage is applied to the paint, electrical current circulates in the paint and the paint is heating.
Current technologies are using metallic particles. These particles are heavy, expensive and difficult to handle and use. On the contrary, this conductive paint is formulated without any organic solvent but in aqueous media, and this paint do not contain metal or hazardous particles. Moreover, this paint is easy to apply to a leading edge of an aircraft and is inexpensive to produce. Finally, this paint is an efficient solution for de-icing while allowing a weight decrease and thus an improvement on environmental impact.
Within
the CarbonInspired 2.0 network in ICA 4 Technica, we demonstrated the potential of nanomaterials for the wastewater treatment. Currently, the polluted waters are subjected to primary and secondary treatments that are able to reduce organic content, but may be ineffective in removing colour because colour is usually due to the presence of highly resistant compounds. However, there is a process called photocatalysis that allows us to destroy the most persistent pollutants through the use of UV radiation and a photocatalyst. When the photocatalyst used has nanometer scale, the efficiency of the process greatly increased. Heterogeneous photocatalysis, unlike most other photochemical processes, is not selective and can be used to treat complex mixtures of pollutants. Within this project has been used to remove colour from an organic dye usually used in the textile sector. As a photocatalyst, it's been used titanium oxide nanoparticles that can be incorporated directly into the water and circulate through the reactor. To perform the photocatalysis, it's been employed a photoreactor consisting of a panel with some tubes through which contaminated water circulates. It can be observed that the process can eliminate more than 90% of colour from the solution in 90 minutes and 75% of the pollution load. In addition, heterogeneous photocatalysis has a huge advantage, the possibility of using solar radiation as a source of ultraviolet radiation and heat, which makes the process have an important and significant environmental value. To prevent the nanoparticles from entering directly into the solution and facilitate their recovery and reuse, in the project we have deposited nanoparticles as continuous coatings on video fibres, which can be easily incorporated into the process. It's important to highlight that the technology can be applied not only in wastewater treatment. The radicals that are generated in the reaction can destroy odours, bacteria, air pollutants and even stain. Therefore, this technology is very versatile and can be used in many sectors, for example, in paints or household cleaning products to improve air quality in a building, or exterior walls to eliminate pollution caused by traffic and prevent dirt from sticking to the facade.